In the last lecture, we learnt about very important concept of organic chemistry, that is aromaticity. Now in this lecture, we will be discussing about concept of hyperconjugation. Hyperconjugation is interaction of electrons present in a sigma bond, usually carbon-hydrogen or carbon-carbon, with an adjacent p orbital or pi bond, which results in the formation of extended molecular orbital. It results in the decrease of energy of the system. Therefore, system becomes stable. The term of hyperconjugation was introduced in 1939 by Robert S. Mulliken when he was working on UV spectroscopy of conjugated molecules. We can understand concept of hyperconjugation with the help of this example of propene. Here we can see that 3 carbon-hydrogen sigma bonds are present at an alpha carbon with respect to this carbon-carbon pi bond. Here we can see how the electrons present in this sigma bond are interacting with the neighboring pi bond and releasing the electrons towards this position. Therefore, this hydrogen atom is acquiring a small positive charge, and because of this, negative charge is developed here. Therefore, this neutral molecule is being changed to the charged structure. Now, the second carbon-hydrogen bond is interacting with the same carbon-carbon double bond and giving another resonance structure. Here, in the same way, the third carbon-hydrogen sigma bond is interacting with this and giving this resonating structure. So, we can see because of the presence of 3 carbon-hydrogen sigma bonds, we are getting 3 resonating structures, and hence stability of the system is increased. If we compare hyperconjugation with inductive effect, we found that effect of hyperconjugation is stronger than the effect of inductive effect. On the basis of inductive effect, we expect that 1-butene will be more stable than propene. Why? We can see here this is the structure of 1-butene and this is the structure of propene. This 1-butene is having ethyl group and this propene is having methyl substituent at this position. We know that ethyl group shows stronger inductive effect in comparison of the methyl group. Because of the presence of hyperconjugation, in case of propene we get more number of resonating structures, and hence because of this interaction there are 3 carbon-hydrogen single bonds are present. Therefore, propene is more stable as compared to the butene, where we are having only 2 carbon-hydrogen single bond at a alpha position with respect to this carbon-carbon double bond. Therefore, propene is much more stable than butene. Hyperconjugation is also known as no bond resonance. This effect is called no bond resonance because here we can see this hydrogen is present here in the form of proton, but it does not leave this position, it remains here. So, there is no bond, but still there is a bond between this proton and the remaining molecule. Therefore, the name comes no bond resonance. Similar effect was also studied in 1935 by Baker-Nathan, and hence the name was given Baker-Nathan effect. Now, what are the structural requirement for any molecule to show the hyperconjugation? Any organic species which is having at least one sp2 hybrid carbon. This sp2 hybrid carbon may be present in the form of alkene, as we have discussed in the last example, or this sp2 hybrid carbon may be present in the form of alkyl carbocation or in the form of free radical. Apart from presence of sp2 hybrid carbon, there should be one alpha carbon having at least one hydrogen atom, so that it will enter in resonance with this sp2 hybrid carbon atom. So, hyperconjugation is of three types. First of all, the common requirement in all the three types is presence of sigma bond. Apart from the presence of sigma bond, there should be a pi bond on adjacent carbon atom. So, it is often called as sigma pi conjugation. This happens in case of alkenes and alkyl substituted aromatic compounds. Next type of hyperconjugation, which is shown by the molecules having sigma bond and a positive charge. This positive charge should be present on vacant p orbital. This conjugation occurs in case of alkyl carbocations. Free radicals also show hyperconjugation because they have sigma carbon hydrogen bond and odd electron which is present in incompletely filled p orbital. So, if these two are present in conjugated positions, that free radical is capable of showing hyperconjugation. Now, the question arises, why is hyperconjugation is stabilized? Here we can see once again the potential energy diagram of hydrogen molecule. These two hydrogen atoms are coming close to each other, and as they are coming close to each other, potential energy of the system is decreasing. After that, suddenly potential energy of the system is increased. So, it is at this much distance that system is stabilized. So, because of the lowering of potential energy, system is getting stabilized. So, if we compare this thing with the hyperconjugation, where we are seeing that carbon hydrogen sigma bond is interacting with the neighboring p orbital, then because of the overlap taking place between two, a new MO molecular orbital is being formed, and this molecular orbital is much more stable than the original orbitals. So, because of the stability we are getting through the formation of MO, hyperconjugation is shown. More the overlap, more the stability of the system. Now, what are the applications of the hyperconjugation? Why this is so important that we are studying this phenomenon? One of the most important application of hyperconjugation is to understand stability of substituted alkenes. On the basis of heat of hydrogenation, stability order of the different alkenes has been found as follows. Here, tetra substituted alkenes have been found to be the most stable, followed by tri-substituted alkenes, followed by di-substituted, and finally unsubstituted alkenes are least stable. We can understand this thing with the help of hyperconjugation. Here is the case of tetra substituted alkene, where all the hydrogen atoms have been replaced by the methyl groups. Here we can see that 3 carbon hydrogen bonds are present adjacent to carbon-carbon pi bond. Here again 3 more carbon hydrogen bonds are present. So, here we can see total 12 carbon hydrogen sigma bonds are present at alpha position with respect to this carbon-carbon double bond, and therefore they enter into the resonance with the system. and we get number of resonating structures. Total there will be 3 corresponding to each. Total there will be 13 resonating structure. Therefore, tetra substituted alkene will be the most stable, and it has been confirmed through experiments also. Because of the presence of this hyperconjugation, a change in the bond length is also observed. On the basis of simple alkene structure, we expect carbon-carbon double bond to be 1.34 angstrom. But because of the presence of hyperconjugation here in case of propene molecule, carbon-carbon double bond is slightly changed because here it is acquiring slightly single bond character. Hence, bond length is increased. In the same way, if we see carbon-carbon single bond, it should be 1.54 angstrom, but in case of propene, it is slightly shortened, and this is 1.5 angstrom. So, this is again happening because this bond is acquiring slightly double bond character due to resonance structures being formed due to hyperconjugation. Stability of the alkyl free radicals can also be understood with the help of hyperconjugation. Alkyl free radicals, they are also capable of showing hyperconjugation because of the presence of carbon-hydrogen sigma bond at alpha position with respect to incompletely filled p orbital. Here we can see in case of tri-substituted alkyl free radical, more number of resonating structures will be possible because we are having total 9 carbon-hydrogen sigma bonds. But here we will be having 3 plus 3, 6 carbon-hydrogen sigma bond, and here we are having only 2 carbon-hydrogen sigma bond at alpha position with respect to the carbon bearing partly filled p orbital, and hence this will be least stable. Reactivity and orientation of electrophilic substitution on benzene ring. We know that alkyl group of alkyl benzene is ortho-para-directing in nature, and it behaves as activating group for electrophilic aromatic substitution reaction. This behavior can be understood on the basis of hyperconjugation only. Here we can see because of the presence of this carbon-hydrogen sigma bond at conjugate position with respect to this carbon-carbon pi bond, it enters into the resonance due to hyperconjugation, and therefore this methyl group becomes capable of releasing electrons towards benzene ring. Electron released towards benzene ring, therefore this benzene ring acquires a slight negative charge, and this negative charge revolves throughout the benzene ring, and now any electrophile species having positive charge can attack on these positions which are ortho or para with respect to this original methyl group, and hence methyl group shows ortho-para directing effect. Dipole moment of molecules showing hyperconjugation is greatly affected because these molecules show charged structures. We can see the example of haloalkanes. If we compare this molecule with the chloroform, we can see here there is no carbon-hydrogen alpha bond on the chloroform, but here in case of this molecule we are having 3 carbon-hydrogen alpha bond on this molecule. Because of the presence of hyperconjugation, it shows charged structure. Therefore, dipole moment shown by the molecule is much more as compared to this molecule. In case of butadiene, we know that these two geometrical isomers are possible. This particular geometrical isomer has planar conformation and this particular geometrical isomer has non-planar conformation. Planar conformation geometrical isomer is much more stable than this one. Another very important application of hyperconjugation is to understand the anomeric effect. First of all, we should know what is the meaning of anomeric effect. The general tendency of anomeric substituents to prefer an axial position is called anomeric effect. For example, alpha methyl glucoside is more stable than beta methyl glucoside. We know that glucose show two conformational isomers, alpha form and beta form. In alpha form, this group lies at axial position, but in beta form, this particular group lies in equatorial position. When glucose is being converted to the methyl glucoside, hydrogen atom present here is substituted with methyl group and we get methyl glucoside. If this particular group is present in axial position, then it is called alpha methyl glucoside, but if this particular group is present at equatorial position, this is known as beta methyl glucoside. This alpha methyl glucoside is much more stable than beta methyl glucoside. This is called anomeric effect. Why this happens? Once again, we will take help of hyperconjugation to understand this thing. Here we can see, in case of axial anomer, these two orbitals are lying parallel to each other. Therefore, hyperconjugation is possible. In case of equatorial anomer, these two orbitals are lying almost orthogonal to each other. Therefore, there will not be possibility of extended MO and hence there will be no possibility of hyperconjugation stabilizing the isomer. Therefore, we can see that axial anomer will be more stable due to hyperconjugation. Reverse hyperconjugation. What is that? This is a phenomenon opposite to the hyperconjugation. In case of hyperconjugation, we have seen that electrons present in the carbon-hydrogen sigma bonds are released towards carbon-carbon pi bond or a p orbital. Here, in case of alpha haloalkenes, the delocalization of electrons occurs towards halogen group through hyperconjugative mechanism, but direction is opposite. Therefore, it is known as reverse hyperconjugation. Dipole moments of alpha haloalkenes are increased due to this phenomenon. Here is the example. We can see that this carbon-carbon pi bond with respect to alpha to this carbon-chlorine single bond. Therefore, here electron release is taking place in opposite direction and it is acquiring positive charge and this chlorine is acquiring a negative charge. Because of the presence of charge, this particular compound shows dipole moment. So, in this lecture, we discussed about various concepts related with hyperconjugation. What are the structural requirements for molecules to show hyperconjugation? What are the applications of hyperconjugation? Why this is so important? Now, at the end of this lecture, we will revise what we have learnt in the last lectures also. We have learnt about the various important concepts related with bond length, bond angle and hybridization. These concepts are helpful to understand shape of molecules. We have also learnt various important concepts like inductive effect, mesomeric effect, delocalized chemical bonding and resonance, which are very important for organic molecules. We have also learnt about the formation of charge transfer molecules, what are their applications, inclusion compounds, concept of hydrogen bonding, different type of hydrogen bonding, their applications, van der Waals forces and their applications to understand variation of physical properties of molecule, concept of aromaticity and hyperconjugation. At the end of first unit, which was based on structure and bonding concepts of organic chemistry, we can see that how significant are these concepts. They are very helpful to understand various molecules covered under the organic chemistry and to understand their unique physical and chemical properties.